So today we're going to learn how to draw Lewis structures or electron dot structures for molecules. You've already learned in the last chapter how to draw dot structures for elements, for specific elements with how many valence electrons that they have around them. And you've also already learned the octet rule that says that most atoms prefer to have an octet or 8 electrons around them in order to be happy and to look like the noble gas. Remember that the one exception to that, the big exception to that is hydrogen, because the noble gas closest to hydrogen is helium. It only has 2 electrons in its valence shell, and so hydrogen wants to look the same. It too will only have 2 electrons in its valence shell, and so it is happy if it has 2 electrons as opposed to the 8 that most of the other atoms want to have. So let's look at a couple of examples here. The first example we're going to look at is a compound called carbon tetrachloride, CCl4. The way that you start by drawing it, to start drawing a Lewis structure, is by looking at your periodic table and looking to see what the dot structure of each individual atom looks like. So carbon is going to have 4 valence electrons. If you don't remember how to do that, you need to go back to the last chapter and figure out how we came up with that. A chlorine has 7 valence electrons, so you're going to have 3 sets of 2 and 1 lone one. Now, again, we had said that it doesn't matter where this lone electron goes. You can put it on the left, you can put it on the right, you can put it on the top, you can put it on the bottom. It doesn't matter where you put it as long as you have 3 pairs and a single. Now, when we start building these molecules, the first thing you want to ask yourself too is, after you get what each individual atom looks like, is which one of the atoms needs the most electrons in order to become happy, to become satisfied. And as a general rule, the atom that needs the most electrons to be happy is the one that you're going to end up putting in the middle, so that it can make the most bonds and share with the most number of other atoms. So chlorine only needs, since it has 7, it only needs 1 more electron to get its valence shell full. So it's going to take its lone electron here and the lone electron here with carbon, and they're going to share those 2 electrons. And then when they share them, what that does is it will make a bond that looks like this. Now you can see that I have 4 chlorine atoms, and so that works out rather nicely, because if I take another chlorine and I put it down here, this time I'm going to take that lone electron, I'm going to stick it on the top because I want to share it up this direction with this carbon. And so these 2 electrons get shared, and I draw a bond between them like that. I have 2 more chlorines that need to be bonded, so one will go here, and these 2 electrons will share and make a bond, and then I'll have a 4th chlorine up here on the top, and these 2 electrons will share and will make a bond here. Okay, so when I'm finished, what I want to look at is to say, do all of my atoms now have an octet of electrons around them? And when you're counting, you want to remember that a bond represents 2 electrons. So if I look at this chlorine, I have 2, 4, 6, 8. This chlorine has 2, 4, 6, 8. This chlorine, again, 2, 4, 6, 8. This one has 8. The carbon in the middle has 4 bonds, 2, 4, 6, 8. So all of the atoms have an octet, so they are satisfied, they have full valence shells, and they're very stable now. So this is the dot structure for CCl4. Let's look at NH3 as another example. This is ammonia. Ammonia is in a lot of cleaners, and it has a pretty pungent smell to it. Nitrogen has 5 electrons around it, and its dot structure looks like this. And then I have hydrogens, and if you remember, hydrogen just has 1 electron in its valence shell. Hydrogen only needs 2 electrons to be happy, so he just needs to share 1 more electron and he's going to be satisfied. And so this electron and this electron here, these 2 will be shared to make a bond. This hydrogen is now satisfied. I can do the same thing on the bottom with another hydrogen. So this electron and this electron will be shared with each other, and that will make a bond here. I can do the same thing on this side and put a hydrogen here. So now I have NH3, I have all three hydrogens have 2 electrons, and then my nitrogen has 2 electrons that I didn't share, plus 3 more bonds. So if I count that, 2, 4, 6, 8, nitrogen has an octet, so it is now satisfied. Okay, let's look at H2S. Okay, hydrogen, again, we've looked at that already. It has just 1 electron in its valence shell. Sulfur has a total of 6. So 1, 2, 3, 4, 5, 6, 2 pairs and 2 singles. It needs 2 more electrons in order to have its valence shell full. So this hydrogen will share its electron with one of the lone electrons on the sulfur and make a bond here like this. And the other hydrogen will come down here and it will share down here. These 2 electrons will make a bond. Both hydrogens are now satisfied because they each have 2 electrons. And the sulfur has 2, 4, 6, 8 electrons. It is obeying the octet rule. It is now very stable and very satisfied. Okay, let's look at a compound called ICl. Here I only have 2 atoms, so there's not going to be one in the middle, so to speak, because they're just going to have to attach to each other. So iodine is in that 7A column on the periodic table, and it has 7 electrons. Chlorine also has 7 electrons around it. And again, I just did this for convenience. I put the lone electrons on the side that's right next to each other so that they will be able to share these 2 electrons and make a bond between them. So the iodine has 2, 4, 6, 8, and the chlorine also has 2, 4, 6, 8. So they each have an octet of electrons around them. So this is the Lewis structure for this compound. We're going to try one more. PHBr2. Okay, this one probably looks a little bit more complicated just because I have 3 different elements here that have to all be bonded together somehow. The H we recognize already as from the other compounds that we've done. We know that that only needs 1 electron to be satisfied. Bromine is in the same column as the iodine and the chlorine. They also are only going to need 1 electron in order to be satisfied. The phosphorus, though, looks like this. The phosphorus has 1 lone pair and 3 single electrons. So it needs, since it has 5, it needs 3 more in order to obey the octet rule. So phosphorus is going to be the element that's going to be in the middle. It has the most it has the most need for electrons. And so now we're going to take these and start pairing them up. So my hydrogen, again, it doesn't really matter where I stick it, and you'll understand why it doesn't matter a little bit later on. But the hydrogen has 1 electron and needs 1 more. So if I share these 2, one with the phosphorus, one with the hydrogen, I'll have a bond here. The bromine, I can put one of them down here. It has 7 electrons. And so this lone electron and this lone electron, one from the phosphorus, one for the bromine, will be shared and make a bond this way. And we're going to do the same thing on this side with this bromine. It will have 1 electron that needs to be shared with this one. Whoops. And so I'll have a bond here like this. Now, always go back and check, is everybody satisfied? So my hydrogen has 2 electrons. He's happy. My bromine has 2, 4, 6, 8. He's happy. This bromine also has 2, 4, 6, 8. So he's happy. If I look at this phosphorus in the middle, I have 2 on the top, 4, 6, 8. So the hydrogen has 2 and everything else is obeying the octet rule. So they are all stable. They're all satisfied. And so I know can be relatively certain that that is the correct dot structure for that one. Always, again, make sure that you count electrons at the end to make sure that you have everybody satisfied and everybody obeying the octet rule.